Good evening. Welcome to today's session and the last session of this course, the problem solving session of this course. Um, as had mentioned earlier in the last session, we'll be doing some revision problems, uh, focusing mainly on numericals uh, from the seventh week till the 12th week's lecture. The week 1 to 6 were covered in the last session, but we'll be again doing the numericals, just refreshing, going through the numericals once again in today's session as well. So, like all the time, I'll be posting this numericals. Please consider doing it so that this could be helpful for you as a practice session to the upcoming exams that are going to happen soon. Um, yes. So maybe before we start our session, we'll wait for a couple of more minutes for some more people to join and then we'll start. Good evening, Anumanta. Okay, so we'll move on to the questions. Uh, yes, so we'll be first dealing with the seventh week's numericals. So I think you have to use this opportunity to practice a bit by trying to do the problems. And then I'll go on with the explanation. Although all these are repeated concepts, we can just go through it once more. So the first uh, set of numericals will be based in this week's lecture will be based on empirical formulas to estimate runoff. So there are four formulas: Barlow's formula, Inglis', Kosla's, and Lacey's formula. And all of these are empirical formulas. So since it is empirical, it is important that you give significance to the units also along with the values that you use in these equations. The units have to be the units that have been mentioned over here. So in Barlow's formula, runoff is equal to K into P, where P is the rainfall and K is the runoff coefficient. For an average catchment or on an average, coefficient is considered as 0.2. And if it is a particular type of catchment they are mentioning in the question, they will also be providing the runoff coefficient with it. So accordingly, you'll have to select out the runoff coefficient and use it. Most of the time, they don't give the runoff coefficient, so you can use the value of 0.2 as a runoff coefficient and use it in this equation. Next formula is the Inglis' formula. And when questions come where you have to use this formula, they will be particularly mentioning whether it is a Ghat area or a non-Ghat area. And if it is a Ghat area, you'll have to use this formula that is used in a Ghat area, and non-Ghat area, you'll have to use this equation. Both the equations, there's only one quantity, one variable, which is the rainfall. And so both the runoff and rainfall you'll be obtaining in mm. In Kosla's formula, again, the temperature is also coming into picture. Uh, so the runoff is found out as a function of the precipitation and temperature, and the temperature will be in degrees Celsius. And in the Lacey's formula, you have the catchment factor, duration, monsoon duration factor, and one particular thing that you have to notice over here is runoff and rainfall are units of centimeter, while in the previous three equations, all three were in units of millimeters. So when if Lacey's formula is used, they'll be giving us the S, which is the catchment factor, F, which is the monsoon duration factor, and probably the values also will be given mostly if they're asking you to estimate the runoff using this equation. Make sure you also don't interchange these two values. S is the catchment factor and F is the monsoon duration factor. So appropriately apply these quantities in this equation, and you need to find the runoff. So here, this is a question that is related to using this formula. If the total precipitation is 100 mm, the initial basin recharge is 20 mm, groundwater accretion is 30 mm. What is the direct runoff? Is it 100 mm, 50 mm, 30 mm, or 25 mm? Okay, this question is more of, I think, this is not using the empirical equation, rather it is making use of the uh, water storage, the water budget equation. Okay, anyhow, just try this problem and so unless the equation is mentioned, there are some general equations with which we will be using, which we will be estimating. So this can, if they're particularly asking you to find the runoff using a Barlow's, Inglis, Poslas, or Lacey's formula, then you might need to use it with those formulas here. But they have just given quantities of variables, so you have to understand that this is mostly involving inflow and outflow components. So you will have to use the water budget equation in order to find whatever quantity they've asked for. So you can try doing this question and putting the answers in here. After which I'll show the solution. Very simple question. This one, you're supposed to find runoff. Now, if you see here, P is the inflow, L, which is basin recharge, is an outflow component. Then groundwater is also groundwater flow is an outflow component. Runoff is also an outflow component. So P is equal to the sum of inflow should be equal to outflow. So inflow is 100 mm, outflow will be 20 plus 30 plus runoff. So in order to find the runoff quantity, you will subtract the sum of these two from P, which will yield 50 mm. Okay, this question is catchment area of 25 kilometers square has an annual rainfall of 750 mm, sandy soil content of 25% and temperature of 18 degrees Celsius. Estimate the runoff by Barlow's formula. So in Barlow's formula, you will have to use R is equal to K into P, where K is the runoff coefficient. Especially over here, since they have not mentioned anything about what kind of catchment it is, we will use the runoff coefficient K as 0.2. And using 0.2, we can multiply 0.2 into 750. Now here the annual rainfall is given as 750. We should use mm as the unit because it's an empirical equation and we need to use the precipitation value in mm. So 750 into 0.2 will yield 150 mm. So the correct answer over here is option A, 150 mm. So when you see that there are lots of other uh, variables that they've given. They've talked about the catchment area, they've talked about sandy soil, temperature, etc. Now, if suppose this question had asked you to use the Kosla's formula, then it you could use this temperature and rainfall to find the runoff. So you should be careful. I mean, keep in mind what all equations you have to remember and the uh, quantities that are used in it accurately and not get confused with the equations. Again, this is also another question. Just now we had talked about the Ingelis's formula, Kosla's formula. Here they are asking us to find the runoff using the Ingelis's formula. Now, Ingelis's formula is talks about Ghat area and non-Ghat area, and we don't need any other quantity except for the precipitation term. So the equation for the Ghat area is P into P minus 177.8 by 2540. Again, here they have given the catchment area, they have given this for a sandy soil content temperature. This you should be careful that you don't get confused with the Kosla's formula, which uses the temperature, and be very careful while when you with what quantity or what equation they've asked you to use in this question. So that was about using the empirical formulas and two types of numerical categories that we see when it comes to this seventh week lecture. Another set of important numerical is this unconfined and confined aquifers, uh, drawdown and height of the well or related to that using the Dipitz equation and the Thiem's equation. So here this type of question will be asked where they'll give you the diameter or the radius of a well of an unconfined or a confined aquifer. Then they'll give the depth of the well, the height of the water in the well, the rate of pumping, which is Q, the drawdown value, which is S1 and S2, and the distance of these observation wells from the center of the well, which is R1 and R2. From this, you will have to find out the permeability or transmissibility depending on what kind of the aquifer. So this one type of problem is a sure shot question. So if you are able to understand and practice this question, it is something you can score very well in. So here again, we see that in wells, when you pump out water, initially the well water is at this static water level. As you pump the water out, it will go down. It will the water will initially go down, creating this cone of depression, and the water of the well will go up to this level. So this distance from the static initial water level to what is the water level at along this cone of depression is called the drawdown. And this water level from the reference point, that is from below, is called the height of the water. And from the static water level is called the drawdown. So questions will be asked based on that. Here also what they have clearly mentioned on what is static water level, what is the cone of depression, and what is drawdown. So it is important you know the difference between what is the height of the level of water and what is drawdown distance. So cone of depression is formed like when water is pumped out, water will flow uh, over the adjacent sides of the wall. It will go down in this profile in the form of a cone. This is called the cone of depression, which this curve is called the cone of depression. This area is called the area of influence, and the radius of this of from the center of the well till this asymptote is called the radius of influence. So here this S term, if there S term is what is referred to as drawdown over here. H will be the height of the water table till the reference surface, and the radius of influence will be the center of the well the distance from the center of the well until this H value, until this cone of depression is reaching its asymptote. Drawdown is the distance of the static water level to any point on this drawdown curve or cone of depression. Then, yeah, pumping rate is Q. R is the radius of the well. Usually they give the diameter, so you should uh, be careful to convert it to radius if uh, that is a quantity that needs to be used in the equation. Now here, again, you can see Q is the pumping rate, R is the distance, R is the distance from the center of the well to that point where the observation well will be. So if the observation well is in this point where you can see the red laser point that I've placed, that will be R. Now observation well 1 is at a distance of R1, means it is at a distance from the center of the well to the center of this observation well. Again, R2 will be the distance of the distance of this observation well from the center of this pumping well to the center of the observation well. Now, S1 will be the distance of the static water table till the drawdown curve. S2, which is representing the drawdown in this well 1. Well 2, the drawdown will be S2, which is the distance from the static water table to the water at that level or the point at the drawdown curve. Now, H1 and H2 will be the depth of the water from the reference line, that is from the bottom of the aquifer or the permeable surface. So H1 and S1 are two terms that can be interchangeably used, because if you minus this whole depth H and S2, you will get H2. If you minus H minus H2, you will get S2. So these two are interchangeable quantities, and all of the quantities over here is been mentioned. So in this question, they've said that the diameter of the well, a 30 centimeter well, means radius is 30 centimeter, and R1 is equal to 21 centimeter, R2 is 71. That is the distance of the observation well 1 and 2, and the drawdown corresponding to these 2 points is 3.5 and 2. That is this this level is 3.5 and 2. Total height is 40 meter. That is initially the depth of the water. This height of the dotted line till this impermeable surface is 40 meter. Q is also given, which is 1,500 liters per minute, and that liter per minute should be converted into meter cube per second, where you will do the appropriate conversions. Then by using this equation, you can also use pi k into S1 square minus S2 square. Since here this is how they have followed, you can refer to this also. So H2, like I said, is capital H minus S2, and H1 is capital H minus S1. Using this in this formula, you will get the you will get the value of K, permeability. Now, if it is a confined aquifer, this term will be replaced by 2 pi t, and here it will be H2 minus H1 by ln of R2 by R1 instead of the square values. So this is how you'll do this problem. This is one set of problems you have in the 7th week lecture. This is also the same thing. Now another set is again associated with the problem that we did initially. Maybe you can try this out, because again I had done one initial problem like this, so probably it will be easier for you. Please try doing it and put the answer in the chat box. you should try doing the problem instead of just saying any option. Uh, that is why these problem solving sessions are kept so that you can also have a guided practice. So this is again using water budget equation. The inflow component is 150 mm. These are the outflow components. So you will subtract 150 minus the sum of these two, and you'll get 80 mm. So, apart from these kind of numericals, the seventh week focuses on what runoff is, what is surface runoff, what is base flow, intermediate flow, what is the runoff theory. There is a runoff cycle you need to learn about. What are the factors affecting runoff? How is runoff estimated? We just now saw estimation using water budget equation. Also, there are various empirical equations with which you can estimate runoff. Then week 7 is also talking briefly about what a hydrograph is and what are the different components of a hydrograph. Then also discussing about the types of wells, a dug well, open well, dug well, deep and in open well and tube wells. In open wells, what is deep well and shallow well? In tube wells, what is deep well and shallow well? There's something called a MOTA layer that is being discussed in this week. So those are some focus points that you can focus on. Then, very importantly, the steady flow in confined and unconfined aquifer. The same portion is being covered in week 6, and it is a continuation to it. The numericals which we discussed right now is part of it. Two formulas are there, Dupit's equation and Thiem's equation for both confined and unconfined aquifer. So terms relating to that, radius of influence, area of influence, cone of depression, what is drawdown, what is the equation for steady confined aquifer and steady unconfined aquifer are all important topics in this week's lecture. We'll be now moving on to the 8th week's numericals. So the first one is on finding out the pi index infiltration indices, which is pi index and W index. So here they'll give the duration of the rainfall, and you understand that the duration of the rainfall is the total time for which this has happened, and this is giving us the interval with which the rainfall is happening. So they have said the rate of rainfall for successive 1 hour periods. So totally for 5 hours, every 1 hour, the intensity of rainfall is changing. That's what they mean. And from this quantities, you're supposed to find the W index. And this is we be using this formula P minus R by T. This is when you have to find the phi index. I'm sorry, but again, if it is W index and if they give a term of initial abstractions, also you will have to subtract that value also from the precipitation value to get the W index. Right now here, since there is no abstraction value, we will consider that term as 0 because they have not mentioned anything about the abstraction value. So even the equation has to be P minus R minus I, but since I is equal to 0, it is P minus R by T. Now, how do we find the precipitation? These values are in terms of centimeters divided by time because W index in phi index is going to be in terms of intensity, centimeter per hour or millimeter per hour. So this P should be in centimeters, R also should be in centimeters. But since the quantities in the question has been given in terms of intensity, it is necessary that you convert it to centimeter first and then uh, use it in this equation. So in order to convert it into centimeters, you will multiply each term with 1 hour because they have said that for a successive 1 hour for a total duration of 5 hours, this storm is happening. So every 1 hour, the intensity is changing. So first hour, it is 5.5, so you will multiply it with 1. For the second hour, you will multiply it with 1. All these 5 quantities, you will multiply it 1, and then you will get the uh, precipitation in terms of centimeter. So precipitation computed like that will be 25.8 centimeter. Now they have also given the runoff. So that when you put 25.8 minus 6.5 divided by T is the effective duration of the rainfall, which is 5 hours. You will get this answer, 3.86, which is the option A. So this is how you do questions for W index and phi index. Other set of questions is using infiltration curves. So one important infiltration curve is the Horton's curve. Horton's equation is in this way. The infiltration at any particular time t is equal to the sum of the final infiltration. Those the infiltration capacity plus FO will be the initial infiltration, and K will be a coefficient. T will be the time for which this infiltration time for which the infiltration is occurring, or after which the whole of the infiltration will occur. So here initial infiltration F naught is given as 5 inches per hour. Then minimum infiltration capacity FC is given as 0.5. And then constant is given, time is also given. So direct substitution will get this. So have an idea about these quantities and the equation as well. This is also one sure question that might come. And also try out the virtual. I think you will have to use the virtual calculator. So make sure you practice using it so that you won't spend a lot of time trying to figure out how to use it for your own online exams. I mean, this taking logs, log is something that you'll need to take for the unconfined and confined steady equation. So you should just familiarize with using that again, using this exponential quantities and all. Something that you'll just learn. You can try it out in advance before attending the exam. Then another set of questions will be using the coefficient of variation. So coefficient of variation and error, optimum number of rain gauges. So this is a formula for optimum number of rain gauges. So that makes use of the coefficient of variations and error, allowable percentage error. And this formula will give the optimum number of rain gauges. So here the question is, they have said there are already 5 rain gauge stations. They have also given the error percentage, and they have given the coefficient of variation value. We are supposed to calculate the additional number of stations. That means the 5 is not an optimum value number of rain gauge for that station. You might need more or less. And in order to get the optimum number of rain gauge stations, you use this formula. N is equal to CV by E the whole square. We get 12 over here, but only 5 is there. So additionally, you have to provide 7 rain gauges. So be careful of not stopping with this number. So there is a tendency that you will apply this formula, find n and write the answer of n. Their options can be given as the optimum number also will come as an option. So when you see the option, you'll see that okay, whatever answer you've got is there in the question. So be careful to uh, to see that you have what they have asked, whether they have asked the optimum rain gauge stations or whether they have asked the additional number of stations required. If they're asking for optimal number, option 4 will be correct. If they're asking for additional number, option 7 will be the correct answer. Option C will be the correct answer. So this is also a problem similar to this. Maybe give it a shot. I'll wait for a couple of minutes. You can try doing this problem and saying which is the correct option. CV by E the whole square is the formula. CV over here is 29.54. E is 10. So it will be 2.954 the whole square. So it will come to around 9 is the optimum number of rain gauge stations. They've said that already 6 is there. So 9 minus 6, 3 might be the answer. The optimum number of stations for an admissible. Okay, they've asked for the optimum number of stations. So 9 will be the answer. So this is a very simple numerical. Please practice. This is again a question on phi index. So you can also try doing this. Okay. So like I had shown earlier the duration successive 1 hour period. Here for a change it is 30 minutes of 4 hours term. So you have to multiply all this quantity by half an hour in order to get it in terms of centimeter. So you add all this, multiply by 0.5 and you'll get this value of P, and P minus R by T. Here R is given as 4 point, no, here the pi index value is given. So 4.5 is equal to 25.4 minus R by T. T is 4. So you'll take this to this LHS side, multiply 4.5 by 4, 4.5 into 4, and then you can find out R is. Now in this problem, we see that there are rainfall intensity varying from 0.8 to 4.6 centimeter per hour. So like usual, we might find out the phi index by multiplying all these values of precipitation, which is 0.8 plus 1.8 plus 3 plus 4.6, 3 plus 3.6 plus 3.2 plus 2 plus 1 into, oh sorry, a storm surface runoff estimate index. Okay, again, this is 1 hour durations. So the sum of all of this will give us the rainfall in centimeters, which is already given here, 20 centimeters. So 20 minus 11.6 by 8 will give us this answer, 1.05 centimeter per hour. But unfortunately, what happens here is 1.05 centimeter per hour. The phi index is defined as the average rainfall above which whatever rainfall occurs is contributing to the runoff. But here, this value of rainfall and this value of rainfall is coming below this average rate. As a result of which, these two rainfall events are not contributing to the runoff. So what we do is we eliminate these two rainfall events. So when we eliminate these two rainfall events, which is 0.8 and 1, we not only eliminate the rainfall intensity, but we also cut short the time during which the rainfall has occurred, because the definition of T value is the effective duration. That is the duration during which the rainfall that occurs contributes to the runoff. So these two events are not contributing to runoff, which means this duration also will not be considered. So 2 half an hours will be, 2 hours will be eliminated from the computation. So what we do is, from the total precipitation, that is 20, is 11.6. Yeah, from 20, you will eliminate 0.8 and 1, 1.8, which is 18.2. And then it's 20 minus 0.8 minus 1, not 11.6. So 20 minus 9.8. Okay, this is also, wait a second. It's 20 minus 0.8 minus 1, which is 18.2. Let me make that changes over here. 18.2, and the runoff is 11.6. So it is, okay, this is not correct. Let me make the correction. This will be 11.6. This will be 6.6. Oh, sorry. This will be 1.1. So this value here is going to be 1.1. Now 1.1, nothing is, we have eliminated this term and this term. All the other values are coming above 1.1. So the phi index will be 1.1 centimeter per hour. So this, I change it here. I think there's a confusion in the last time when I discussed this also. Probably did change the value. Okay, so this is the answer. So the final answer would be 1.1 centimeter per hour. Again, a similar question. Here, what they have asked is, assuming that pi index value is 3 mm per hour, there is an initial loss of 0.8 mm. And they have asked to find out the total rainfall, the net runoff, and the W index. Now, this initial loss is going to be what is used is in the W index. So let's see how they find out. So here time is given as a 140-minute duration storm with 20 minutes interval. So 3 mm per hour is occurring in the first 20 minutes. After that, again 3 occurs, 9 occurs, 6.6 occurs, 1.2, 1.2, and 6. So that is how it is provided over here. First 20 minutes, this is the intensity. 40 minutes, this is the intensity. 60 minutes, 9. After say 80 minutes, it will, until 80 minutes, 6.6. After 80 minutes, it will become like this. Depth of the rainfall, you will multiply 3 into 20 by 60, because it is given as mm per hour. So you have to convert this minute into hours. So 23 into 20 by 60, 3 into 40 by 3 into 20 by 60. Here we are taking care of the interval, not the cumulative time. So be sure to multiply these quantities by 20 by 60, not by 40 by 60 and 1 hour and 1.5 hours. So the total precipitation is 10 mm. We found that out. Total rainfall. They have asked to find out the net runoff. So in order to calculate the net runoff, they've given the phi index value as 3 mm per hour. But unfortunately, 1.2 and 1.2 is coming under 3 mm per hour. So we will eliminate these two values. Also, we'll eliminate 3 and 3 because it is also not considered 3 is uh, contributing to it. So only these values are left. So 9, 6.6 and 6. See, from 10 they have eliminated 3, 3, 1.2 and 1.2. So totally you will get the effective rainfall as 7.2 mm. Now 7.2 minus R by 20, 40, 20, 40 and 60, 1 hour. So 7.2 minus R by 1 is equal to 3. So 7.2 minus 3 is equal to 4.2 will be the runoff value. So in order to find the W index, the total precipitation 10 minus this runoff is taken and initial loss, zero point 0.8 is taken divided by the duration for this effective rainfall is considered, not the total duration that is provided over here. So that is how you'll find the W index. So week 8, apart from these numericals, what is rainfall? What are the various forms of rainfall, the different types of precipitation? How is rainfall measured? Recording gauges, non-recording gauges. How is mean rainfall estimated? What is normal rainfall? How is missing rainfall estimated? You will have to study about the double mass curve, then also about yeah, you'll have problems relating the optimum number of rain gauges, problems related to that. Index of wetness, that is also another set of focus point. Then how rain gauge networks design based on the IS guidelines for plain area, for areas less than with elevation less than 1,000 meters, for areas which is having elevation more than 1,000 meters according to guidelines. What is the number of rain gauges that need to be provided? Then they are also talking about infiltration. What is the difference between infiltration rate and infiltration capacity? What is the relationship between infiltration and rainfall intensity? Then the SPY index, W index questions. So this will be the focus points for week 8 lecture. When we move to week 9, we have these kinds of questions. Again, very similar to this. There are methods to estimate groundwater recharge, and this is using the water storage method or groundwater storage method. This is same as the water budget equation. Here, the change in storage is a difference of the inflow minus outflow. Inflow has, first of all, they have an initial water level of 90 meter, but during the month, it is receiving water, 160 mm of water, and 80 mm of water is extracted. So 160 minus 80 will be the change in storage. So if the had 90 meter initially, then how much is the additional water level? How much is the water level going to increase? You'll have to add the storage value that you get. That is the only additional element that is being used in here. Again, same type of question using the uh, groundwater level water storage equation of recharge. This is, I think, if you familiarize this question, a similar type of question, maybe with the values differently, will only be asked. Uh, then I think on an average from there will be numericals because I think how many questions are going to be there. I don't know about the number of questions, but I think out of all of these, if 12 weeks lectures are using say 24 numericals, around 20 numericals can come, I believe so. So the easy way to score marks is to familiarize with the numericals because it is something that you can be thorough on. Only the values are going to change. So, okay, for a change, this question, This question is, excuse me. Okay. So in this question, here till now they were asking about these quantities were given in terms of and depth, uh, units of depth. Here they are giving it as rate. So in order to convert this rate to depth value, you will always have to multiply by the time and divide by the area. That is only when you get this meter cube per second in terms of meter or mm or whatever. So this 1.5 you will have to multiply by duration. So they have, so some value of day or duration will be given. So they have asked for 1 day. So if you multiply 1.5 into 24 into 60 into 60, you can convert this into volume. The volume to convert into depth, you have to divide by the area, which is also given over here. So that is the only variation in this problem. Otherwise, everything else, the concept uses again net inflow minus net outflow is equal to change in storage. This is using the groundwater level fluctuation method. Till now, we talked about the groundwater storage method, which is based on the water budget equation. This is another method to estimate recharge, and it is done using these terms: uh, specific yield, change in storage, the return flow, and TP, the time for return flow. So two types of equation used. One is this groundwater level fluctuation method. So here specific yield is given. Then 50 centimeters is the change in water level, that is delta S. Since return flow due to irrigation is negligible, this quantity becomes zero. So that is why you can compute it as a product of these two values. So this is another type of numerical that can come from the 8th week lecture. Sorry, 9th week lecture. Again, this week's lecture is focused on different types of resources, groundwater resources in India. How much percentage of groundwater is used globally for irrigation and for other purposes? How much is used in India? Then what is the annual replenishable groundwater? What are the different ways to recharge, natural ways to recharge groundwater? Artificial methods are covered in the 10th or 11th week. Then how the different methods to estimate groundwater recharge. We just checked two methods just now. Then groundwater assessment units. There are units into which the watershed, sub-watershed, command area, non-command area, into blocks, taluks, and all of that. So that divisions. Then concept of annual uh, replenishable recharge water, concept of TAR, and how is TARR computed. So these are some focal point in the 9th week's lecture. Fortunately, 10th, 11th, and 12th week doesn't have any numericals. It's full of theory. In 10th week, what is the necessity for groundwater management? What are the different scientific methods of groundwater management? What is a watershed? What are the different categories? Micro watershed, macro watershed, all of that classification, the groundwater resource management techniques, then various stages of groundwater management development, sustainable and non-sustainable water resources management. These are the focus points in the 10th week's lecture. In the 11th week, it is mostly focused on artificial recharge of groundwater and rainwater harvesting. And in 12th week, it is the impact of climate change. What is global warming? What is greenhouse effect? What are the greenhouse gases and and some details regarding the greenhouse gases? What are the effects of global warming on water resources? Effect of climate change and global warming on groundwater resources? And what is the projected climate change in India? So this is about the 7th to the 12th week revision points focused on numericals. Now week 1 to 6 was already covered, but again I'll just I mean this week's presentation will have all types of numericals that are covered in week 1 to 12. So if any of you are focusing on solving numericals, you can make use of this slide, this PDF for PPT. So in week 1, same water budget equation only. If this one problem you learn, I think one or two numericals surely you will be able to solve. We had seen inflow outflow units. You convert it into units of volume over here and find out what is the final storage. So initial storage is given, inflow rate is given, outflow rate is given. So you will convert it to volume, and that volume change in volume is going to give us the change in storage. Now another quantity given here is the initial and the final storage. So initial storage is 17.5 hectare-meter, which means 17.5 into 10 to the power 4 meter cube. So what is the final storage you can get after you calculate the change in storage. Then this is again the same problem. Another simple format of inflow outflow. Inflow here is precipitation. Outflow here is seepage loss and evaporation. So those components are used in this chain in this equation, water budget equation. So P minus E plus G, or P minus 18.5 minus 2.5 minus 9.5 will give us the uh, quantities for change in storage. Week 2 doesn't have any numericals. It's mostly on water cycle for different types of rocks, consolidated, non-consolidated. All of those are covered in week 2. In week 3, again, this is also one very simple area where you could score marks, as well as numerical, this one about hydraulic gradient and hydraulic conductivity, focusing on the Darcy's equation. So Darcy's equation is velocity of water flowing through an aquifer is a product of its hydraulic conductivity and hydraulic gradient. Hydraulic conductivity is also called coefficient of permeability. Hydraulic gradient is the change in the pressure head, um, pressure head to the length of flow. So I is representing hydraulic gradient, K is representing hydraulic conductivity. So these quantities will be given in the equation. You just have to multiply and you will get the velocity. In the same way, if they are asking about the discharge, you have to multiply the cross-sectional area and you will get the discharge over here using Darcy's equation. So that is one, this is the only type of numerical that is coming in week 3 lectures. So if you learn this numerical again, these two equations and its relevant terms, it is one sure area of scoring marks. In the 4th week's numericals, they are making use of these formulas to estimate the groundwater recharge. The Bhattacharya formula. There are various empirical formulas that is being used, so you'll have to familiarize with those. Again, Darcy's equation is being covered in this. In the 5th week, this is more related to the aquifer hydraulic conductivity and transmissivity. This part is additionally coming along with the hydraulic conductivity and Darcy's equation in this 5th week's questions. So transmissivity, the definition, and what is the formula. They will be giving you the thickness of the aquifer and hydraulic conductivity. You just have to put it directly in the equation and find out. Always, for irrespective of what numerical, always be careful about the units that are being used, what units are being given in the question, and what unit is being asked for in the answer, and do the appropriate conversions. One very important thing that you always have to keep in mind. This is another area, the relationship between porosity and void ratio. Porosity is equal to E by 1 plus E, and void ratio E is equal to N by 1 minus N. So those are the portions that are covered in the 5th week. In the 6th week, about the travel time of water and the travel time of tracer and actual velocity. So this question is on the finding the actual velocity when the travel distance and the tracer traveler time is provided. Just the normal velocity equation, distance by time. In in this again, hydraulic conductivity and hydraulic gradient is given, but hydraulic gradient is given in a different form. It is given as the change in head by length. I had said hydraulic gradient is the change in head by length here. So how do we find the change in head? The upstream and downstream, what is the head? You will subtract both of it and you will get what is the difference in head divided by the travel distance is also given over here. So you can find out what is the uh, velocity, what is the hydraulic gradient, and multiply it with the hydraulic conductivity to get the velocity. So this is the same as Darcy's equation, except instead of directly giving the hydraulic gradient value, we are giving the change in the head at two levels and the length between those two levels. This is for the finding out the traveling time of water, distance by velocity into porosity. So basically, that will be it. Uh, this session has covered almost all the kind of numericals that will come from the 12 weeks of lecture series. So I wish you all the best for your exams. If you have any doubts, you can ask or you can leave the session. That will be also good. Yeah, sure, you can ask. And are you asking about this PPT or which PPT? These PPTs are already uploaded in the portal. You can every week's PPTs has been uploaded. Every week's video as well as PPT is uploaded in the portal. You can access it to that. Which PPT are you talking about? The problem solving session or the lecture series? Which PPT are you talking about? Is it the lecture series that is taken by Professor Prasoon, or is it the problem solving PPT that you're asking about? Problem solving is already there in the portal. If you see, there is something called a problem solving session in the Swayam portal. You need to open that. If you go to the Swayam portal, you can access it through that. And regarding the lecture material, there is something called transcripts in the portal again. If you download that, that has all from lecture 1 to lecture 60, all of the PPTs in that PDF document. I'm surprised you don't know about it. The videos of this lecture and the PPTs that I'm showing at every week is uploaded in it, in the Swayam portal. Maybe I can share you a. Do you want me to share a link? I'm surprised that you don't know about it. Please go to the Swayam portal, log into your Swayam account, and you'll see week by week from where you access your lecture videos itself. In the end, there will be something called problem solving session. When you click that, it will share. It will take you to a Google Sheet. That Google Sheet, week wise, all the PPTs and the videos have been uploaded. And if you want the PDF of the lecture material that is also there under the heading transcripts. Okay, Hanumanta, I guess that's it. Thank you for attending all the sessions regularly. Yeah, thank you also to be actively participating. I think you have been one of the regulars for all of the session. So today will be my last class. All the best for your exams and do well. Do the best of your capability. No problem. You can try focusing on whichever portions you're comfortable with. There are a lot of people who find numericals more easier. So this lecture session, these problem solving sessions are also for them. So if remaining revision I have done for all of the other portions, so it will be beneficial for everyone. Okay, thank you, Hanumanta. There is a forum, you can post in your doubts in the forum.